Welcome to the Deep Dive, where we pull back the curtain on the technology you use every single day. Just look around you, or even at the device you're listening on right now. Inside that sleek box, there's this invisible, really intricate world just humming along. It's like a tiny city of parts working together, often totally unseen. So today, we're going to try and demystify that hidden universe. We'll explore how all those different computer parts actually work together, from the brain doing the thinking, right down to the cooling systems, keeping it all from, well, melting down.
That's right. Yeah, this deep dive, we're really aiming to shed light on the big players, the CPU, memory, storage, but also those unsung heroes like the motherboard, the network stuff. And crucially, we had to talk about keeping things cool, thermal management. Because honestly, heat, that's often the biggest bottleneck you hit.
Right. And we've got some pretty interesting sources lined up for this. We're looking at some quite technical papers on advanced CPU cooling methods, but also a fantastic Reddit explain like I'm five thread, some really great analogies there, and insights from industry folks like Kingston and Corsair.
Yeah, the goal today, it's pretty straightforward, really. We want to give you some solid foundational knowledge about what's actually going on inside your computer. So by the end, you should hopefully feel a bit more informed when you're looking at specs or upgrades, and maybe just appreciate the complexity humming away there.
Okay, so if we're peeling back the layers, we absolutely have to start with the main act, the conductor, right? The central processing unit, the CPU. It really is the nerve center, isn't it? Making everything happen.
It is. Yeah, at its core, the CPU is just incredibly fast at following instructions. I mean, the amazing part isn't just that it follows this four-step cycle, fetch, decode, execute, store. Yeah. It's that it does this billions of times, every second, turning abstract code into, what you see on screen. It's lightning fast. And that's driven by things like the control unit. Think of it like the orchestra leader and the ALU, the arithmetic logic unit, handling all the math and logic stuff.
Billions of times a second. That's wild. Okay, so when we talk CPUs, you always hear cores and gigahertz. For us regular users, what do those actually mean in practice?
Great question. So cores, think of it like hiring extra workers for your office. More cores mean your computer's brain can literally think about more than one thing at the same time. Or tackle a really complex single job much faster if it can be split up. So yeah, generally more cores equals better multitasking.
Okay, more workers. Makes sense. And gigahertz, gigahertz. Is it just, bigger number equals faster computer? Simple as that.
Well, mostly yes. A higher number usually does mean faster processing. Gigahertz, it represents the speed of the brain, literally how fast it can cycle through those instructions we talked about. When you see talk of a better processor, like, say, an Intel i3 versus an i7, that generally means a faster, more efficient worker overall. But clock speed, the gigahertz number, it's really only useful for comparing chips from the same family or generation. It's a bit like comparing engine RPMs. A high RPM on a small engine doesn't automatically mean more power than a lower RPM on a huge truck engine, Yeah. Different designs.
Ah, okay, that distinction is important. Different designs matter. So inside the CPU itself, there are also these super fast little storage spots called registers. I've heard them called tiny scratch pads right on the chip. What's their role?
Exactly. Registers are these special, incredibly fast, but very small, temporary storage areas right on the CPU die itself. They're not like main memory. They hold the absolute immediate instruction or piece of data the CPU needs right now, like nanoseconds away. So you have things like an accumulator register that holds calculation results, or an address register keeping track of where to find the next bit of data in memory. They're vital for speed.
Okay, so CPU has its internal scratch pads, the registers, but where does it keep the stuff it's actively working on and all our files? This brings us to memory versus storage, and yeah, understanding this difference, it's really key to getting why your computer feels fast or slow.
It absolutely is. It's fundamental. So the big distinction is RAM, random access memory, versus long-term storage. Think of RAM as your actual desk, or maybe a big table where you lay out everything you're working on right now. The key thing is it's volatile. Power goes off. Everything on the desk vanishes. Gone. It's a temporary but super fast workspace. All your open programs, your browser tabs, the document you're editing, that's all sitting in RAM for quick access by the CPU. More RAM means a bigger desk, right? So you can spread out more work without things getting slow or cluttered. Directly impacts speed and multitasking. Storage, on the other hand, that's your filing cabinet or your bookshelf. It's non-volatile. Power off. Doesn't matter. Your stuff stays there indefinitely. This is where your operating system lives, your apps, all your photos, videos, documents, everything permanent.
That desk and filing cabinet analogy, yeah, that really works. It clicks. So, okay, restarting your computer is maybe like a quick swipe across the desk, clearing some stuff off. A full shutdown is like properly cleaning and organizing it. But what about that Windows Fast startup thing? Does that change how the desk gets cleaned?
That's a really good point. Yeah, precisely. Windows Fast Startup isn't quite a full clean sweep. It's more like taking a quick photo of your messy desk before you turn the lights off, and then just putting things back roughly where they were when you turn them back on. It saves a snapshot of the system state, which makes booting up faster. Sure, it's convenient, but it doesn't give you that truly fresh, clean desk start that a full shutdown and boot does. That's why sometimes, for troubleshooting, people turn it off. Now, looking at the filing cabinet side, long-term storage, we've seen a huge evolution there. You still have the traditional HDDs, hard disk drives. These use spinning magnetic platters and little read-write heads that move back and forth. They're big plus points. Still cost-effective, especially for really large amounts of storage. Great for archives, big media files. But the downsides are obvious. They're slower because things have to physically move, and those moving parts can, well, eventually fail. Then you have SSDs, solid-state drives. These are based on flash memory NAND technology, the absolute key difference. No moving parts at all, and that translates directly into huge benefits. Way faster boot times, opening files, loading apps. They're much more durable, too resistant to bumps and drops. Plus, they use less power and are silent. Now, they used to be much more expensive per gigabyte, and people worried about write cycles, how many times you could save data. But honestly, with modern SSDs using techniques like wear leveling to spread the writes around, that limited lifespan thing is much, much less of a concern for typical users today. They last a long time. And then, of course, there's flash memory like USB sticks and memory cards. Super versatile, portable, non-volatile, solid-state storage. Their advantages are obvious. Convenience, plug and play, tiny size, durable, work across tons of devices, great for moving files around or small backups.
Okay, so lots of options. For us, the listeners, trying to choose maybe for a new build or an upgrade, what's the takeaway? How should we prioritize?
Right, connecting it back, SSDs. Absolutely essential for your operating system and your main applications, games too. That speed makes a massive difference to the feel of the whole system. High performance, you need an SSD. HDDs, they still have their place for bulk storage where speed isn't critical. Think large movie libraries, photo archives, system backups, best cost per gigabyte, definitely. And flash drives, memory cards, perfect for portability and quick transfers. Oh, and one important side note. If your computer runs out of RAM, that desk space, it can use your storage drive as virtual memory. But accessing the filing cabinet is way slower than using the desk. So while it prevents crashing, using virtual memory heavily makes your computer feel really sluggish. Always better to have enough actual RAM first.
Good tip. And storage tech isn't stopping there, right? I hear about even faster stuff coming along.
Well, yeah, definitely. We're seeing emerging storage technologies that are really pushing boundaries, like NVMe. That's basically a much faster way for SSDs to talk to the rest of the computer using the super fast PCIe connection directly instead of older interfaces. The speeds are incredible. And then there's tech like 3D XPoint, which Intel and Micron developed. It's aiming to kind of bridge the gap between RAM and storage. It's faster than traditional SSDs, lasts longer, and it's non-volatile like storage. It can really change how systems are designed in the future, offering almost RAM-like speeds for persistent data.
Wow. Okay, so we've got the brain, the workspaces. Now, how does everything actually connect and talk? The internal communication network and how it reaches the outside world.
All right, this is where the motherboard is central. Think of it as the city's road network. It's the roadway that allows all of the other parts to communicate. Or, using that office analogy again, it is the office building itself. It dictates what kind of CPU fits, how much RAM you can install, what slots are available for cards. It's the main circuit board that ties everything together physically and electrically. Compatibility starts here.
And speaking of communicating, how does my computer actually talk to the internet or other devices on my home network?
That job falls to the Network Interface Card, or NIC, sometimes called a network adapter. This is the hardware that lets your computer physically connect to a network, wired or wireless. It handles the practical stuff like making sure data gets routed correctly, packaging it properly for transfer, managing the connection. There are basically two main flavors. You've got wired NICs, usually using an Ethernet port and cable. These offer really stable, high-speed network access. They're super reliable, which is why you see them everywhere in offices, data centers, and why gamers often prefer them for low latency. Inside desktops and servers, these are often PCI Express network adapters for top speed. Then you have wireless NICs for Wi-Fi. They use radio waves, obviously, giving you that cable-free convenience within range of your router or access point. And for flexibility, especially with laptops or older machines, you can get USB network adapters, both for wired Ethernet and for Wi-Fi. Just plug them into a USB port.
Okay, so if I'm buying a new machine or maybe looking to upgrade my connection, how do I choose the right NIC? What factors matter?
Good question. First, decide. Wired for stability and maybe top speed, or wireless for convenience. If wired, what speed do you need? Standard gigabit Ethernet is common, but faster options like 2.5 Gbps or even 10 Gbps are available if your network supports it. Check the interface too, usually built-in PCIe card or USB. If wireless, look at the Wi-Fi standard. Wi-Fi 6, or even the newer Wi-Fi 7, offer better speeds and handle crowded networks better than older standards. Then consider cost, brand reliability, and maybe extra features like built-in Bluetooth, which some NICs include. It's often a trade-off. Built-in NICs are convenient for everyday use, but buying a separate expansion card like a PCIe one can give you better performance, more features, or an easy upgrade path later.
Seems like NICs are getting smarter too. I've read about some future trends there.
Absolutely. The future is quite exciting. We're seeing NICs pushing for high data rate support, adapting to 5G speeds, really leveraging Wi-Fi 6 and beyond. Security is huge too, so expect more robust cryptographic devices built right into the NICs. And then there are smart NICs. These are really interesting. They have their own processing power designed specifically to take networking tasks off the main CPU. Things like data path processing, encryption, firewalling, the NIC handles it, freeing up your main CPU to do other work. Very cool for high-performance scenarios.
Okay, fascinating stuff. Now let's shift gears a bit. Let's talk about the specialist component for visuals and the absolute lifeline keeping everything running and, crucially, cool.
Right. So the GPU, the graphical processing unit, this is also on its own dedicated video card. Think of it like hiring a specialist artist for your office. It's another person at another desk who can paint what the work of the CPU asks really quickly. It has its own powerful processor optimized just for graphics and its own super fast memory called VRAM. This means the main computer, the CPU, and the system RAM doesn't have to struggle with drawing complex images or video. The GPU handles it. The result is much faster and crisper visuals. Absolutely essential for high-end gaming or high-end graphics and video work. It offloads that specific intensive work.
Right, like going to a specialist mechanic for an oil change instead of making the general dealership mechanic juggle it with everything else. Much more efficient for that task.
Yeah.
Okay, and what provides the actual power for this whole complex operation, the thing that keeps the lights on safely?
That critical role belongs to the PSU, the power supply unit. It's really the heart of your computer. It takes a high-voltage AC power from your wall outlet and converts it into the various lower-voltage DC currents that all your different components need: motherboard, CPU, GPU, drives, fans, everything.
Yeah.
Its job is vital, providing clean, steady power. Fluctuations can cause instability or damage. Good PSUs also have built-in protection features: overvoltage, short-circuit protection to safeguard your expensive parts.
So what does this mean when choosing one? Getting the wattage right seems important. How do you figure that out?
Yeah, matching the wattage to your components is key. It's like you said, trying to power hungry parts with a weak PSU. It's like asking a 6-year-old push a full-size truck. It just won't cope, leading to crashes or instability. On the flip side, getting a massively oversized PSU for a basic system, that's like asking a large football player being asked to push a really small smart car. It'll work, sure, but it's inefficient and maybe overkill. The goal is enough power for everything running at full tilt, plus maybe a little extra headroom, say 20–30%, for stability and potential future upgrades. You'll also see ratings like ADP-LUS, bronze, silver, gold, platinum, titanium, or cybernetics ratings. These certify the PSU's energy efficiency, how much power drawn from the wall actually reaches your components, and sometimes noise levels too. Higher ratings generally mean better quality components and less wasted electricity as heat.
Heat. Right, that brings us back to a huge topic. All these components, especially the CPU and GPU working hard, they generate a serious amount of heat, don't they? Keeping them cool sounds like a massive engineering challenge.
It absolutely is. It's a constant battle. You mentioned Moore's Law earlier, packing more transistors into smaller spaces. That directly leads to higher module-level heat flux. Basically, more heat concentrated in a tiny area. And this has been steadily increasing for decades. If you can't get that heat away effectively, the chip will slow itself down to avoid melting. That's thermal throttling, or could even suffer malfunction or permanent damage. So cooling is non-negotiable. The most common method, historically and still widely used, is air cooling. This uses fans, often combined with heat sinks, those finned metal blocks. That's a heat sink. It just increases the surface area to transfer heat from the chip into the surrounding air, which the fan then blows away. It's cost-effective, relatively simple. A step up from basic heat sinks are heat pipes, often integrated into air coolers now. These are clever sealed copper tubes with a liquid and a wick structure inside. They use a passive evaporation condensation cycle to move heat very efficiently from the CPU block up to the cooling fins, offering significant performance gains over just a solid block of metal with no moving parts themselves. But for really high-end CPUs or overclocking, air cooling sometimes isn't enough. That's where water cooling or liquid cooling comes in. These systems use a pump to circulate a liquid coolant through a block mounted on the CPU, then through a radiator where fans dissipate the heat from the liquid. Water is much better at absorbing heat than air, like 3,500 times better capacity. So liquid cooling offers a big drop in thermal resistance, leading to lower temps, often quieter operation than high RPM air coolers. And we're seeing even more advanced stuff now. There's the active liquid heat sink, ALHS, basically integrating the pump right into the heat sink block, making it more compact. Then you get into really exotic territory like immersion cooling, literally submerging the components in a special non-conductive fluid. That offers incredible heat transfer because the coolant is in direct contact everywhere. And even thermoelectric cooling tech. These are solid-state devices, no liquids or moving parts besides maybe fans on the hot side. They use electricity, the Peltier effect, to create a cold side directly on the CPU, actively pumping heat away. They can keep temperatures incredibly stable.
Wow, from simple fans to literally dunking the whole thing in liquid or using solid-state chillers. That's quite the progression. But you mentioned complexity and cost earlier.
Exactly. Each step up from air to heat pipes to basic liquid to immersion or thermoelectric significantly improves cooling potential. But each step also brings new complexity to designs that directly relates to the cost. So more parts, more potential points of failure, higher manufacturing costs. But as heat output continues to rise, these more advanced solutions are becoming less of a luxury and more of a necessity to actually get the performance we expect from top-tier components.
What a journey. Okay, so we've gone from the computer's brain, the CPU and its workspace, RAM and storage, through the communication hubs, the motherboard, and NICs, all the way to the specialists like the GPU and the critical lifeline of the PSU, plus this whole sophisticated world of climate control with cooling. It's a lot going on in there.
It really is. And our hope, really, is that this deep dive has given you a clearer picture, a more informed view of all that intricate work happening inside your devices. Because, knowledge is great, but it's most valuable when you can actually understand and maybe apply it. Hopefully, you've got a bit more appreciation now for that silent complexity.
Yeah, absolutely. So what does this all mean? Maybe the next time you boot up your computer or hear the fan spin up, you'll feel a bit more connected to that hidden world working away for you. It truly is a marvel of engineering, always pushing forward.
So here's a thought to leave you with. Considering how CPU heat output keeps rising, and we always want smaller, faster devices, which of those extreme cooling methods we touched on, maybe full liquid immersion or those thermoelectric coolers, which one do you think might actually become mainstream in regular personal computers, say 5 years down the line? And maybe more importantly, how would a shift like that fundamentally change what our future computers even look like, or what they could do?